Okay, all of you are, hope you are able to listen to me, and then uh, so are you able to see me and listen to me both? Uh, I will ask one or two people. Vedant Srikant,
Yes, sir. Yes, sir. You're
are
audible.
you able to see me and listen to me?
Yes, sir.
Both. Okay. Devendra Duba, Devendra Duba, Devendra Duba, Devendra Duba.
Hello, sir. Hello, sir. Yes, I can hear you, sir.
You can see me also.
Yes, sir.
Fine. So fine. It is 5 past 10:30. That means 5 minutes. I've just waited for people to come. Now still some few people have to come, but anyway, 5 minutes we waited. I feel that is sufficient enough. Okay. Now, as we discussed yesterday or previous class, in this course. Okay, so now I will put share the content which I would like to talk. Please wait. Okay, are we able to see the PPT which I put, course contents?
Yes, sir. Sir, can you please record this session, sir?
Yes, that I shall do it. Definitely, I shall do that things once. Okay, I put the recording just now. Okay, then afterwards, can I put full screen? I don't know. I'll just let me see. Okay. And then okay. 1 minute. I don't know where it went. Okay. Okay, so I started recording now, just now, and then course content I put. I hope all of you are able to see that. And then now I will previously in previous class I told what is briefly. Now I'm putting the things in a more better manner. So now, as we discussed in previous class, now we are talking about what is the content of this course. So as I told you, first and foremost, we should understand what is nano and what is crystal structure of the common materials. And then how packing density, I will let you know why we have to discuss all these things. Surface to volume ratio. So basically, then afterwards, nanomaterials, some of the metals we take gold, silver and platinum, and then properties of those materials, those materials, nanomaterials will study. As we discussed in previous class, nanomaterials are very attractive, not because only because of miniaturization, but their important properties and very exotic. Exotic means new and unpredictable properties. Why? Because as I discussed in previous class, in introductory point of view, gold, as you know very well, it is a yellowish metal and it is a conducting. So what do you mean by conducting? It conducts electricity. That's what it is. Gold also, silver also, it is platinum. All metals conduct electricity. Why? We will talk discuss. So that, but if you go into the nanometer range and few nanometers, let us say less than 5-10 nanometers, then they can become what is called semiconducting and also insulators. So we can have insulator gold, we can have semiconductor gold or silver, that which is unknown previously. So that means it's really new what is called property. So which is really astonishing for the newcomer naturally. because you might be listening to all the years that go metal is a metal and semiconductor is semiconductor and those things. So that means we can cross the boundaries from metal to semiconductor to insulator. So that is if we once we prepare smaller and smaller nanoparticles. So it's really something which is to be understood and to at least to know what it is. Then afterwards we talk about semiconductors, and then as I told you, semiconductors also very important thing. And then we discuss what length scales and semiconductors. As I discussed in the previous class, what is meant by nanoscale and what is meant by material. So do you feel 100 nanometer, 100 nanometer particle, 200 nanoparticle? Okay, I think somebody is doing mischief. Please don't do that. Okay, they are putting my what is called muting of my mic. So please don't do that. Okay, please let us be honestly listening to us, and then I should explain to you. You should listen. Okay, let us be honest to both of us, so that we can discuss some physics or technology, whatever you call that. Okay, so please don't make any mischief. Don't put my things moving. Then it will be. I mean, I will recognize it, but it takes a few seconds for that thing. Okay, so now that means basically, I hope if somebody is not able to listen to me, please let me know. Okay. Fine. Now that means basically we are now we can discuss what is called carbon nanostructures are very popular because now popular in sense even newspapers and magazines also talked about carbon nanostructures in their science and technology section in their daily paper or magazines. So that's why it's called popularization of science or technology, whatever you call that. So in that way, I hope you people might be knowing that about carbon nanostructures. Then preparation of the carbon nanostructures and properties and applications. What are the carbon nanostructures? Basically, you may be aware that graphene, carbon nanotubes, those things we will discuss. Okay, then afterwards, as I discussed already in previous class, that the characterization techniques means STM, AFM, SNOME, and SEM, TEM, and all the things, because these these experimental systems are very important to understand nanomaterial properties, different properties of nanomaterial. First and foremost, we should know what is size and shape of the nanoparticle. So those type of things can be understood through these experimental techniques. So afterwards, we will discuss some applications like sensors. I think you may be aware that sensor means basically a sensor means basically a sensing of any electrical or magnetic or biological, what's called biological or any type of signals. So that means we have to create signals and then sense those signals by these nanomaterials. So plasmonics very important area that we will discuss when we are discussing nanomaterials, metals. And then plasmonics is very important subject wherein we can have lot of sensors, gas sensors, biosensors, chemical sensors, and many type of things, electrochemical sensor like that thing. Then applications in electronics, because basically we are in electronics department. Then we will discuss about electronic devices applications of this nano. See, please don't try to feel that it is only a science, nothing technology. Don't feel in that way. Lot of scientific and technological applications are they coming and expected in every branch of science, So what it means by saying that electronics, I think all of you are knowing MOI structures because you are 7th semester, so you may be having a good course in devices. So MOI structures. So when MOI structures are there means metal oxide semiconductor structures or CMOS. Okay, those structures basically those devices are enhanced by these nanomaterials. So a lot of applications are there. So don't have any feeling that nanoscience is only a science, no technology. No, a lot of technology is there. Lot of electronics technology is there. For example, all of you are knowing that electronic chips means all of you know that see with gadgets which we are utilizing, even computer and then cell phone and other things, they have what's called electronic chips. So means what is happening? There are different types of what's called blocks, electronic box in blocks, not box, BLOCK, blocks arranged in the on the substrate. So we have to have what is called communication between one block to another block. So all those things generally people do with electrical communication, let us say electrical contact. So then people try to previously people made through what is called copper. Now people are using aluminium. So now some more important thing happening is that what's called optical communication between what's called the blocks in the chip. So those type of because electrical contacts in between the blocks of the chip will have some limitation because electrical contact means electricity is passing through. Then what happens? So then ohmic losses will be there. So that means heating will be there. So those type of considerations will limit the usage of what's called the electrical contacts in the chips. So that's why people are wanting to change into the optical because there is no what's called deleterious effects of the optical communication. So there are a lot of applications in electronics also. OK, we try to introduce some of these electronic devices applications of in nanotechnology. Then afterwards, I'm putting. Let me tell one thing. The course content which I'm putting is only a brief. OK, not necessarily. Don't feel only fine, only like that thing. Only it's a brief content to show to you what is the what are the topics that are there in this subject. OK, in this course. Then afterwards, we are putting references. So introduction to nanostructured nanoelectronics, science and technology, engineering applications. OK, this fellow. Then introduction to nanoscience technology workbook M. Kuno, Donald semiconductor physics and device physics, Rao and other people. The chemistry of nanomaterials, synthesis, properties, applications. OK, so nanoscale materials. Jan Whaley and G. Cow, nanostructure, nanomaterial synthesis, properties and applications, and nano, the essentials, understanding of. OK, T. Pradeep he is a professor in IIT Madras, and then you may be aware of Professor C.N.R. Rao, who is Bharat Ratna and well known in scientist worked in IISc Bangalore and JNCSR Bangalore, and he is well known in his work solid state chemistry, and a lot of has having lot work in nanoscience and other things also. OK, so these are the books which we follow, and as and when I'm trying to teach one particular topic, then I will let you know what is the book, and then I will put that book also in the meet means in this thing such that you can access that. OK, so these are the things which I would like to say. So if you have any doubts, please let me know. I would like to know if you have any doubts about what contents I told just now. OK, so I would like to listen from you whether you are listening to me and if you have any doubts about what I told just now. Suti Sandeep Kalyankar.
Yes, sir.
So do you have, I hope you should have listened to me. Do you have any questions to ask?
No, sir, no doubts.
OK. Pranav Kabra. Pranav Kabra. Pranav Kabra.
Yes, sir, I'm here, sir. I don't have any doubts.
Okay, so in this way, so I just presented the proper what is called what are the topics we discuss in our course. Okay, now I will be putting actual subject. Okay, are you able to see the what is called PPT?
Yes, sir.
Okay, it's fine. Thank you. So one fellow is telling means I take it as a everybody else is able to see and listen to me. OK, so that's important thing. If by any chance if anybody is unable to see, please let me know. It may be possible my problem or your end problem. Then but I should know that you have any problem anything. OK, so please let us have good communication among ourselves. Now, so just now, as I told you, the crystal structure is an important topic to discuss materials. See, one thing more will tell you this subject is some more of materials. And then in previous class, I made one comment saying that the society which masters the materials is a master of technology. Not just putting MTech or BTech doesn't mean that we are very good in technology. As I hope you are aware of that thing because you are seniors enough to know what is what. So that means basically without materials, because whatever it is seen in as a device is a material. So without material, if you just talk something, that means you are not actually in control of the device which you are talking. What just you are talking, somebody did device and we are just talking about it, some other properties. But a person who is actually doing the device and having the device in his hand is actually powerful. Is it not? So that means basically Western countries are powerful. Why? Because they are mastered. They are mastering and they mastered and mastering the materials. Now, after doing the materials understanding and then devices, they are doing some other important things. But unless otherwise, we also have that tendency to master, to understand and understand the materials and their properties, how to make different materials, synthesis. So even if we talk so great thing doesn't mean much because we don't have anything with us. We can eat food only when we make food. OK, so OK, I don't like to go further about it, but it suffices to say materials are very important things. So in that materials also, so crystal structure. So now what is meant by why we should talk about crystal structure at the beginning of the course? So any material is composed of atoms or molecules depending on the material we are talking about. So now talk about, let us say talk about copper because we know that's why nothing else. So copper atoms are there. So how copper atoms are arranged in the material depending on the what is called how they are arranged with respect to one another, how close with respect to one another, how far with respect to one another, then those things are very important. Because then what is the properties of the materials? Properties of materials are basically the conductivity, electrical conductivity, thermal conductivity. OK, then afterwards in semiconductors, conductivity comes electronic conductivity, hole conductivity, because there are two, as you know very well, there are two carriers, electrons and holes. So in electric field conditions, how electrons will travel across the sample, across the material, that is an important, that is called conductivity. So conductivity is an important thing. OK, so conductivity of electrical conductivity. Similarly, thermal conductivity. OK, specific properties, specific heat property. There are so many types of properties. Magnetic properties. OK, you know magnetic materials. iron, cobalt, nickel, those are all magnetic materials, ferromagnetic materials, as you know very well. So that means how magnetic property is being exhibited by those materials. How can we understand those magnetic materials, let us say? So those type of things we require. So that means magnetic materials, then superconducting properties. Okay, how I think you maybe might have heard about superconducting. Last class, if I remember, aware of superconductors. So afterwards, insulators. So insulators, all these materials are very important. All of you are might have studied what is called power electronics. I don't know whether electronics people do power electronics, but electrical people do power electronics. If I understand more. But also people should have some understanding of power electronics. So for in power electronics, basically very high power means basically voltage is high, then the insulators are most important. OK, is it not? If I nothing to say further about it, silicon, without silicon, there is no electronics, as you know very well. So that means this silicon is a material. So that means basically what I want to convey to you is that basically materials are important. Without materials, without understanding the materials, we can't just do anything, but we have to borrow and then beg, borrow or steal, nothing else. OK, coming to the point. So now, then why should we talk about crystal structure? Now, how the atoms in a material or in a unit of the material are distributed. So that is important thing. So when you are there, when you in previous year or so, when you are coming to the physical class, sitting in the class in the institute. So once you people come into the classroom, you will sit according to your choice. OK, now that means what is happening? You are sitting in the chairs according to your choice, and then accordingly only you can communicate to one another. If you want to talk to one person who is somewhat far away from you, you may be able to talk because you are human being. You can shout whatever, but that means what I'm trying to say is that basically the communication or interaction. OK, the word I'm putting is interaction. Interaction means between communication is one type of interaction. So interaction between two atoms, depending on how apart they are arranged, how closer they are arranged or how distant they are arranged. So that means, and one more thing I would like to say, once you come to class, your chairs are put in a proper, very structured manner. That means in rows and columns, everything is there. I hope I need not explain what is row and what is column. You know better because you are seniors enough to understand somewhat things which I am not able to put in the view graphs. OK, so hopefully to next class I will put the view graphs about that thing. But today I don't have that. So now that means basically, so in a good rows and columns, the structured rows and columns, the chairs are arranged, let us say. Then you people without hopefully without changing the what is called disturbing the rows and columns, you go and sit in your chairs. Then what happens? You people are what's called constituting what is crystal. What do you mean? What is called crystal? That means distance between two chairs is same. Consecutive chairs is same. OK, and distance between two rows or two columns is same. OK, then that is what it. So that's called crystalline structure, ordered structure. OK, crystalline structure, ordered structure. So that means basically a crystalline structure is a structure wherein atoms are arranged in rows and columns. OK, rows and columns in a regular order. Distance between 2 points, two atoms are is same. Two consecutive atoms is same. OK, both translation point of view or a rotational point of view. OK, I hope you people are able to imagine what I'm trying to talk. OK, if you feel that you require some view graph, I will put it next class. OK, so that means one atom So okay, now you may be aware what is meant by crystal. What is meant by crystal? Crystal is basically lattice plus basis. I think you may be aware of this nomenclature and understanding. I don't be underestimate you. I hope you know because of your physics classes in your first year or 12th class, whatever it may be. Also, please recollect what it is at that time, what it was discussed and all those things. That means crystal. What is crystal? What is lattice? Lattice is the structure of imaginary points. Since we don't know, actually we don't know crystal, is it not? How can we know the crystal structure? Any one of you are aware of the terms, aware of experimental techniques wherein we can get crystal structure? Anyone? Please put your hands up if anyone knows how to understand what is called how to what is the experimental technique to know the crystal structure? Yes, very good. That is X-ray crystallography is a very important technique wherein what is called very good. So wherein we can understand experimentally we know what is crystal structure. What is crystal means how distance between two atoms it is there. How that is most important thing. And rows and columns how they are arranged. All those things we know. Okay, so now, okay, before going, okay, I thought of putting it somehow. Okay, I just 1 minute, I will tell you. Before putting in this, I would like to say one thing more. You see, are you able to see here, all of you? Hello?
Yes, sir.
Okay, you see here, it's called transmission electron micrograph. So it is basically individual CDSC means quantum and sorry cadmium selenide. Okay, CDSC means cadmium selenide. You can see this is we will talk about what is transmission electron microscope later, but we can see with that technique we can see the cadmium selenide quantum dots how they are arranged. You see here, are you able to see? I'm putting my I hope you are all of you are able to see. So now you see here cadmium selenide quantum dots. So that means basically they are arranged very good ordered manner. You see in this near this micrograph, every point, every white point is cadmium selenide. So that means here we can in this area, the cadmium selenide quantum dots are arranged in a very regular manner in a both what's called the rows and columns. So this type of arrangement is called crystalline structure. Crystalline structure. So moreover, see you can see in this view in this picture there is one.
Sir, muted.
So this is basically comparable to the size of this crystal. So that's why it is called 5 nanometer. Area is basically hexagonal area. So hexagonal structure. So area we can calculate. So that means this much area nanostructure is there. So that means basically every white dot is a cadmium selenide quantum dot. So now these quantum dots are arranged in a very highly regular manner, both in what's called rows and columns. So that's why it's called crystal. Crystal. So, but thickness of the crystal is very small. That's why it is called two-dimensional crystal. It's called two-dimensional crystals. So that means what is meant by three-dimensional crystal? Three-dimensional crystal is what is called. I think you are aware what is three dimensions. What all we see in the nature with the naked eye is a three dimension. It has length, breadth, and height. So that is called three dimension. But here only length and width are there, but there is no height, or height is very small. So that's why it's called two-dimensional structure. So that means two-dimensional crystal structure. So crystalline structure. I hope you are getting my point. It's a crystalline structure. So that means basically, so this is called crystalline material or crystalline structure. OK, but it is the nanoparticles. Nanoparticles are quantum dots. We will talk about what is that thing, all those things later. But try to see here. I would like to see only one thing. What is that? The atoms are arranged in a regular fashion, both in X and Y direction. And in Z direction also they are arranged. So that means it's a three-dimensional crystal, otherwise two-dimensional crystal. OK, so this is what I would like to say. So that it is called crystalline structure. Why it is called crystalline? I'm talking more times same thing because I want to put your this concept to you later. I mean in your mind. So that means why it is called. You think you see you put your mark in one white dot. Then second white, second dot, third dot. So both are arranged what is called in a regular fashion. OK, so that's why it is called crystalline structure. And one more important thing, this way of defining the crystal as if the atoms are arranged in regular fashion and further in all three dimensions X, Y, Z to the infinity. You have to understand ideal crystal is a crystal wherein atoms are arranged in a regular fashion in all three dimensions to the infinity. To the infinity means x axis is minus infinity to plus infinity, y axis is minus infinity to plus infinity, z axis is by minus to plus infinity. Why? Infinity means too much distance. But that's the ideal crystal. Why we have to discuss, or why we have to say to the infinity? Because I will tell you later, but I can make one statement. Surface is also a defect. Surface is also a defect. How it is there, we'll talk later. So that means what happens? A real ideal crystal doesn't have any defects. The atoms are arranged in a regular fashion in all three dimensions to the infinity. That is called crystalline structure, ideal crystalline structure. But real crystals are, we cannot make a crystal which is having infinite dimensions in all three directions, is it not? Which is impractical. But real crystals will have some finite dimensions, finite XYZ dimensions. OK, so one more important thing I would like to say. So please put your focus on one particular cadmium selenide dot, means one white dot. Then you can see that you translate it to some direction, some distance. Then you can find next dot, again next dot, next dot. That means basically, if you take one atom or one, here in this case, cadmium selenide quantum dot, and then you can find another dot. If you translate it to the left, right, all those things, some distance. So that means it's called crystalline. It is called symmetry. It is called symmetrical. OK, I hope you are understanding my point. So translational symmetry it is called. What is translation symmetry? One atom, or one, here in this case cadmium selenide quantum dot, if it is moved by unit distance, you can find one more dot. Again unit distance, translation means moving. So one more dot like that. That means basically you can find quantum dots or atoms in regular intervals. That is called translational symmetry. Translational symmetry. Then one more important thing. Okay, what is that? Okay, just put your focus on one particular quantum dot. Then imagine one axis perpendicular to that. Then rotate it what is called 90°. Then you can find this dot. Rotate it 90°. This thing again. So this is a hexagon. That means 30 degrees. Okay, so like that thing. Okay, you will be getting 60 degrees. So 6 will be like that. Okay, so that means basically what I'm trying to say is that if you imagine one perpendicular axis and try to rotate the crystal, you will at a regular theta, you will find one more atom or one more quantum dot in this case. So that's called rotational symmetry. Are you getting my point? It's called rotational symmetry. So then one more thing also we can say. Okay, take one line of the quantum dots in this case, and imagine you are arranging one what is called one mirror. Then what happens along that what's called line of the atoms. Imagine one you are arranging one mirror in the line of atoms, along the line of atoms. Then what will happen? You can see in the mirror exactly mirror image of the atoms which are in front of that. So that means both basically if you take one axis this side and left and right side both are arranged similarly. So that's called mirror. These crystalline materials follow what's called symmetries. Follow symmetry. I hope you understand what I mean by symmetry. I hope you know that thing. Okay, if you don't know what is symmetry, please try to say that. I hope you are getting me. Are you understanding?
Yes, sir.
Okay, please. If you have any doubts, please let me know. Okay, I will clarify. I will try to see more explanation. I will give more explanation for that. So okay, so now that means basically, so that means a crystalline structure can have symmetry. What are the symmetries? The symmetry considerations: translation symmetry, rotational symmetry, and mirror symmetry. Are you getting my point? So now we have to define a crystal structure or crystalline structure, a structure which follows symmetry. Okay, is a structure, a crystal structure which follows all symmetries, all types of symmetries, which is translation symmetry. I hope you know what, as might have understood what is translation symmetry, and then rotational symmetry and mirror symmetry. So that means a crystalline structure will have all these three symmetries. So a material in which atoms are having all these three symmetries is called a crystal. Okay, I hope you are getting my point. So now that means I'm defining the crystal structure. I am defining a crystal structure in such a way that not in a traditional point of view, which in a traditional point of view, what is said, basically atoms are arranged in a regular fashion in all three XYZ directions to the infinity is called a crystal. That is a conventional, maybe 12th class definition. At that stage, if you say that, that is sufficient. But at this stage where you are BTech and 7th semester, wherein within 6 months more you will be getting BTech degree, if you tell same thing, it may not be that much good. You are not listening, understanding more into that. Now you should try to say what is a crystal. It means a crystal is having which follows all three symmetries. What is that three symmetries? That translation symmetry, rotational symmetry, and mirror symmetry. Then it is called crystalline structure. Okay, then now there is okay. I hope you understand what I'm trying to convey to you. Okay, okay, fine. Okay, so that's called crystalline structure. Then afterwards, now I would like to talk about polycrystalline structure. What it means by polycrystalline structure? Poly means several. Crystalline means, as you told just now, crystalline or polycrystalline or crystalline structure means what? Now in this material, in this type of material, there are so many crystals. So in one small crystal, there are so many other type of crystals. What is meant by that thing? What is meant by that? So what is meant by that means to take now total thing is one crystal. OK, you are able to see this is totally, we can say this is one crystal because at every point, the symmetry is being followed in a similar fashion. Means similar symmetry considerations can be utilized to describe the structure in all parts of the crystal. It is called crystal, one crystal. Then afterwards, what is polycrystalline? Poly means several. Several crystals are there. In one crystal, several crystals are there. So what is it? Just now, what we told just now, a crystal is a crystal where symmetries are followed. Let us say, I'm just for the sake of understanding, I'm telling one part of this crystal is having some type of symmetry. In another part of the crystal will have some other symmetry, and another part is some other symmetry. Another part is some other symmetry. OK, I hope you are getting my point. So what is meant by that thing? Let's say in a simple term, in this part of in this area, the distance between two atoms is, let us say, I'm just for sake of understanding, I'm telling 1 nanometer. In this part of the crystal, it is 1.2 nanometer or 1.5 nanometer distance between two consecutive atoms. So here this is a 1.5 or 2 nanometer. I'm just telling. So what? But in this some particular area, the distance between two consecutive atoms is fixed. In this area, this is some other distance between two atoms is fixed. It is some other atom. So that means in this, but in total area, there are different areas wherein the crystal parameter means distance between two atoms will be different. So that means this area is acting like a one crystal. This area is acting as one crystal. This area is acting as one crystal. So in this total crystal, there are, let us say, for the sake of present example, there are, let us say, 3 crystals are there. So that means each crystal is called crystallite. So that means there are, let us say, I'm just for sake of understanding, I'm telling in this crystal there are 10 crystallites. That means 10 crystals having some dimensions wherein crystalline nature will be different. OK, are you getting my point? Are you getting my point? So that type of material is called polycrystalline. So polycrystalline. So what is meant by that? In what way it is different from crystalline material? Basically, it is different from crystalline material because now instead of total area is having same crystal structure or same symmetry, following same symmetry, but only parts of the crystal has having some parts of crystal will have different type of symmetries. Here there is a different symmetry. Here this is different symmetry. Here there is different symmetry. Here there is a different symmetry. So that means basically this is what is that means what is happening in the same macroscopic crystal. So microscopically that the different type of crystals are present. So this is a macroscopic crystal. OK, macroscopic, as yesterday I told, is a measurable length and width and height. So that means measurable means some dimension. In that there are smaller crystals are there, which are called crystallites. So that means crystal property of in this area is different from in this area. different from in this area? Let us think. I'm not saying here, but let us think that crystal property of one area is different from crystal property of other area. But in that particular area, crystal property is same. In this particular area, property of the crystal is same. In this particular area, the property of the crystal is same. So that means in this total crystal, we can think of total crystal as if in this crystal there are so many crystals. They are small crystals are called crystallites. So that means this crystal composed of different crystallites, and each crystallite is a crystal. What do you mean by crystal? Crystal means it will follow the crystalline symmetry. What it means basically, if a material, if some volume of the material has having different volumes, having different crystalline properties, then it is called polycrystalline. Okay, I hope you are getting my point. So that means then how can you say that what in terms of symmetry, what we can say in totality, crystal will not follow the symmetry, but each crystallite has its own symmetry. In that, each crystallite will have all three symmetries, means translation symmetry, rotation symmetry, and mirror symmetry. So this is one crystallite. So again, this crystallite has all three symmetries. So that in totality, they are not following, this crystalline is not following what is called the symmetry considerations. But in that, each crystallite is a crystal again. Okay, so that means polycrystalline means in a given volume of the material, there are so many types, poly means so many crystals. Each crystal or each crystallite has its own symmetry. Okay, now whether having total volume, similar symmetry is better, or this type of thing is better? To be ideally, same crystal, one crystal having same symmetry throughout the volume is the best to happen. But it is difficult to get. So that means how can you then you should be asking, first of all, how can we make a crystal? How can we make a single crystal? How can you make a crystal? What are the problems in the crystal making of the crystal? How can you get this type of very good crystalline structure in the real? How can you prepare a material having very good crystalline structure? Can we prepare? Yes, we can prepare. And it is a perfected art. It is nothing new in that. It's a perfected art. So people know how to make all types of materials, crystalline materials. But for every practical purpose, we may not be requiring what is called crystalline materials, because they are costly. It's a making of a single crystal material is a costly affair. It's a highly what's called, and further we require very high cost experimental techniques. So that's why, depending on what type of device we want to make, we can relax the crystallinity of the material. So for very good what's called the electronic chip, we may require good crystalline structure, highly uniform crystalline structure throughout the length and breadth and width of the material in all three dimensions, because that is that type of very good important devices can be made sometimes, but it is too costly. So that's why we may have to reduce the requirement of the quality, and then actually we have to pay price for that. Price in sense, not money. I'm talking about the quality of the device, those type of things. Okay, so basically science and technology is basically also dependent on the economy of the situation, because if I have 10 rupees, I may have some less quality material, maybe 100 rupees I should have get good quality. But what you require depends on what type of device you want to make, how can you utilize that, how can you utilize that material to make a device which is having very great characteristics or comparable like that thing. I hope you are getting my point. So that means basically what I would like to say. So that means crystalline quality is best for crystalline material. Polycrystalline materials are not that much good, but why they are not good? First of all, why they are not good? Why crystalline materials are the best materials? Because now coming to the point. So why important? First of all, how can we understand the properties of the materials? Properties of the materials depends on electronic behavior. Means electrons. All of you are knowing. Okay, electrons are holes in semiconductors, electrons in the metals. Okay, then copper plates in superconductors, magnons in magnetic materials. So depending on what is the charge carrier, so charge carrier properties will determine the property of the material apart from crystal structure. So now if I want to know, if you take a crystal structure, a crystal having very good what's called crystalline properties, very good symmetry, then how can we get a best electronic properties? Because now let us say now this structure is there, this crystal is there. Now conductivity. Talk about conductivity. What do you mean by conductivity? Electrical conductivity. So what is electrical conductivity? Electrical conductivity means electron is moving. So for you, but I think all of you knowing how to make Ohm's law, how to make what's called electrical contacts. How you make electrical contacts? See, these are all important things for a if you want to do something. These are all important things. Okay, so how to pass electricity through a material? Let's say copper single crystal or copper crystal. So we have to make two contacts. Then connect it to the voltmeter or volt source. Then electrons will. So voltage will across the sample. Then electrons move. Okay, is it not? You know it. So that means they should have some electrical contacts to material. Okay, so without going further in that, so that means what somehow you initiate electron flow in the material. Then what will happen? Electrons will pass from one end to the other end of the material. Then how they will go? They will go that electron is moving. Okay, from one atom to another atom. Then that means what is happening? So then because of that, electron is moving from here to here. But let us say it's a polycrystalline material. So if it's a polycrystalline material, then how it is moving now? How can we say from one crystallite to another crystallite? What is happening? Electron is seeing one type of crystal material, crystalline properties in this area. Now coming to the adjacent area, which is having different crystal property or different what is called distance between among the atoms. Here there is some distance, here some other distance. Then what will happen? There is a boundary between this crystallite and this crystallite. Then what will happen? It has to electron now can move from here to here because of it has to change its properties according to the crystal of this crystal. So that means it loses. So you know electron is a wave. So a wave loses its some energy. So that means now how much amount of energy or electron energy is entering into crystallite, one crystallite, another crystallite is changing and it losing because of the boundary between two crystallites. So that means at the boundary, it's called crystallite boundary, it loses its momentum and other things. Okay, we talk later. That's all physics. So that means basically what it means by that, what I'm trying to say, because crystalline materials will have best possible properties, but polycrystallines will have better properties than what is called crystalline materials. But we require all the type of materials. Okay, did you understand? Hope you understand my point? Okay, so I have some work at 12 o'clock, so I will stop after 10 minutes more. Okay. Okay, now that means basically what is happening? So now that means, okay, now you saw two types of materials. What is that? First is crystalline material and there is polystyrene material. Crystalline material and polystyrene material. What the first is, then you know, symmetry property is broken. Symmetry property is broken in the crystallite boundaries of crystallites in the polystyrene material. Is it not? I hope you are getting my point. Symmetry is being in the polystyrene material. Symmetry considerations are good only in the within the crystallite, but across the crystallite, from one crystallite to another crystallite, the symmetry property will change across the boundary. Okay, I hope you are getting my point. Then now think about the atoms are not at all arranged in a regular fashion, even in small crystallites. Now atoms are not at all arranged in a regular fashion. Distance between two atoms is irregular. One is let us say 1 nanometer, or there is 2 nanometer, and there is 10 angstroms. I mean 1 angstrom, 2 angstrom. So that means distance among the atoms is randomly changing. Randomly changing. That is called amorphous structure. That is called amorphous structure. That means atoms are not at all arranged in regular fashion. It doesn't have what's called fixed distance between two atoms, and it doesn't have follow the translation symmetry. It doesn't follow the rotational symmetry. It doesn't follow the what is called mirror symmetry. Then it is called amorphous. And sometimes in amorphous crystal, that's called, so that means it's totally disordered. See, all of you might be remembering that once you come to the institute at 10:30 AM and 3 PM, there are two breaks, means class breaks. Then what happens from AB5, if you want to go outside, so naturally one gate is there, through that gate you will go outside. Then actually what will happen? Then people are moving at random, is it not? There is no regular thing. Some people want to go this side, that side, that side. Then so many people are there also. So then you have to then one fellow, let's say one of you want to go outside at that time. So you cannot walk straight. You can walk in a very zigzag manner, is it not? So that means electron will also move in the amorphous material in a zigzag manner. It cannot move in a straight line. Okay. Then what will happen? It loses its momentum quickly. It loses its momentum quickly. Momentum means energy. So that means but sometimes in amorphous materials, in a local order can be there, but total there can be some local symmetry or local order, but in totality there is no order. But in strongly disordered systems, more than amorphous, then there is no symmetry at all. I hope you are getting my point. So in this way, we can categorize the materials according to its structure, crystal structure. First is crystalline structure, then is polystyrene structure, then amorphous structure. In amorphous structure, there is no symmetry considerations because there is no fixed distance between two atoms, fixed angle between two atoms. Okay, so then at that time electron moves in a zigzag manner and then it loses its energy very quickly. It loses its momentum very quickly. But in polystyrene, across the crystallite boundaries, electron loses its energy. Once it enters into next crystallite, then it moves in a good fashion, in a regular, what's called straight line motion. But between one crystallite and the crystallite, it loses its energy. It will have what's called, let us say, a wave is passing through one medium to another medium. Then what will happen in the near the boundary of the media? Then the energy will be what's called scattered or reflected, all those things. That means electron energy as a wave, as you know, will also have what's called it will also suffer backscattering, or backscattering means reflection, or front scattering, forward scattering, all those things. Then it loses its energy. Okay, but it loses only at the boundaries of the crystallites. But there is no loss of energy in the crystalline material. Why? Because symmetry is there. But in amorphous material, total loss is there. Total means we should not say total, but there is also some conductivity will be there, but lesser than crystalline and polycrystalline. Okay, so and strongly disordered structure also will be there. It doesn't have any local order, also will not be there. It's totally disordered structure. So now I will talk once more: crystalline structure, polycrystalline structure, amorphous structure, highly disordered, strong disordered structure. Okay, in this way we can have 4 types of materials according to the crystal structure or according to how atoms are arranged with respect to one another. Okay. Now you tell whether in what way, I mean, what about, I mean, do you have any doubts? Please let me know. Hello? Tarun Telerja? Do you have any doubts? Siddharth Dange? Siddharth Dange? Ayush? What happened? Are you aware? Or you are
Yes,
there or still?
Hello.
Please tell me any doubts?
No, sir. Sir, could you please share the PDF that you are referring right now? So this book on Teams.
Definitely, I do that. Today, by today evening, or I mean, after some time, I will do that. Okay.
Okay, sir.
Vedant, Srikant.
Yes, sir. No doubt.
Ariman Banerjee.
No doubt, sir.
Okay, so now it is 11:37 because I have some work, important work in this thing around 12 o'clock. So I have to prepare something. So I will stop here. Please don't go. I will take attendance now. What is happening? Why it is not taking? Okay, I have taken attendance. If you don't have any doubts, you can leave. Again, we will meet on Tuesday evening.
Thank you, sir.
Okay.